In the last video, I set you up, and I set your mentality up for what's to come, really. That's exactly what I did. I hope at least that's what I did. And here on the screen, what you're seeing is carbon hanging out with a different type of crowd. These crowds are typically transition metals or alkali metals or alkaline earth metals. And you're seeing a difference in polarity or electronegativity. And in each case, the metal carries with it the partial positive, and the carbon carries with it the partial negative. And all of this is due to the electron sucking device that we call electronegativity. Okay, so carbon in each one of these cases has a higher electronegativity. That higher electronegativity sucks the electrons toward the carbon, which make it partial negative, and that exposes the metal a little bit more, and that makes it slightly positive. So magnesium and zinc and lithium and aluminum and copper and lead and cadmium and mercury and palladium and ruthenium, all of these, they all work the same way. Well, what that means to us in the long run is that carbon, because it's slightly negative, and the metal, because it's slightly positive, carbon no longer is acting in its traditional role. This negative is acting like all negatives do. And that negative, is a nucleophile. And nucleophile and an electrophile and a pedophile, if you remember that from Orgo 1, it kind of gives us an idea of the definitions of these things. Electrophile is electron-loving. Nucleophile, maybe neutral-loving. Pedophile is probably okay. So this carbon is going to act as an electrophile. Nah, wrong. Normally it does. But not in the world of organometallics. So carbons will act as nucleophiles because they're negative. And that nucleophile is going to go out and say, okay, I've got what I want, but I want more. And it's going to go out and try to find another atom that it can rip electrons from. Well, this electrophile is electron-loving. So on its search, more, it could run across this electrophile here. And this electrophile wants electrons. The nucleophile has extra electrons because it's negative, and it's on this search, and it finds this electrophile, and they fall madly in love. And that carbon looks at that electrophile, and it says, oh, I like you a little bit better. I like you a little bit better because you maybe bring more to the table. You maybe have more of what I want. I mean, maybe it just found a doctor that's single and hot and has a large bank account, and that carbon's going to go, oh, whoa, I've hit the jackpot here. And then it looks at that poor little metal that was in a relationship with it, and it looks at that metal and it says, we tried this. It just didn't work out between us because I found a doctor that's got a bigger bank account, and that's all that I care about, so metal, you got to go. And that metal leaves. And that's what we see over here to the product side. We see a molecule now that has a new electrophile on it because this electrophile was more attractive. And think of it almost like a substitution reaction. It seems like everything goes back to a substitution reaction. And that metal has been substituted now for this new electrophile that was brought into the system. And that poor metal, whatever that metal is now off on its own. And it's single. And it's boo-hoo-hoo-hoo-hoo because it just broke up with carbon. It broke up with carbon simply due because that electrophile had more than what that metal could offer it. That's kind of sad. Oh, what a disaster. It's like a Nicholas Spark book right there. You know, they just need to talk to organic chemists to write these romance novels. I think that we could give them very great ideas. So these metals all will behave the same way, but look at the notation here, folks. We often use Y for nucleophiles, E for electrophiles. We kind of realized that in Orgo 1. And now we're bringing metals to the table. I've always said organic is not rocket science. It shouldn't be. And M is going to represent a metal. Now, they could have made your life difficult here and chose another completely different letter, but they didn't. So whenever we see M, that is the traditional run-of-the-mill template, a letter that we often use for any of the metals that you see here or any of the metals that's not shown here that participate in organometallic reactions. Okay, the other thing I want to show you on this slide are nomenclature rules. You know, very often before we talk about reactions, we talk about nomenclature. That's kind of the setup of the lectures, at least if you've had me for 251. We talk about naming them, then we talk about reactions. So naming alkanes, naming alkenes and reacting alkenes, naming alkynes, reacting alkynes. So here, before we react with metals, we want to talk about how we nomenclate them. How do we name them? Very easy. What we do is that we find the longest carbon chain, like here, 4 carbons in a row, and we use the word butyl, just like before. And then we name the metal, lithium. That's it. That's all we do. So here, 2 carbon chain, ethyl, and then this MgBr, we can name that together. So MgBr is called magnesium bromide. Ethyl magnesium bromide is the name of that metallic organic. Here, this is a propyl unit. That propyl unit is in parentheses. There's a 2 on the outside. That 2 is a di. 2 groups. So dipropyl, cadmium. And then here, to the end, we have CH3CH2, which is ethyl. And there's 4 of these. So that's tetraethyl. And we name the metal, which is lead. So butyl, lithium, ethyl magnesium bromide, dipropyl cadmium, tetraethyl lead. The basics of the nomenclature has not changed, nor will it really ever. This is kind of set in stone. That's the great thing about learning IUPAC. So other than this, I'm not really going to throw you curveballs as far as nomenclature goes if that's what we have to do in an example problem. They keep it basic. They keep it very short. They keep it very simple. Not too many crazy things happen. You just got to keep in mind you name the metal at the very end. Simple as that. Okay, so let's do maybe an example. Not a big deal. So let's say that we had to draw a structure from a name. The first one, butyl lithium. Well, we just kind of saw that, didn't we? Yeah, I'm just testing you. Did you pay attention? So butyl lithium. Butyl is 4 carbons, 1, 2, 3, 4, and then a lithium. There you go. So going backward is just as easy, if not easier, because the name is already given to you. You just got to put the pieces together. If you put the pieces together, folks, you've got the right answer. Really no more complicated than this at all. Okay. Now, let's start with our first set of reactions. And 2 we're going to group together because they behave very similarly. And the first organometallic reactions that we will learn will be those based with lithium and those that are based with magnesium. All right, so lithium is, of course, Li. Magnesium is Mg. These are the M's. These are the metals. These are what carbon will hang out with when carbon decides to act a little differently and get out of hand. Completely different carbon shows through. And these metals allow carbon to become a negative charge, a nucleophile at that point. So let's talk about these reactions and kind of discover what we're going to be in for as far as these reactions are going to be concerned. So the first thing that you have to realize, first, you don't really order these. Okay, I don't order a bottle of a organomagnesium compound. I don't order a bottle of organolithium compound. For this reason, a lot of times they're very unstable. Unstable means that they kind of react very easily, and what they react with is going to be a problem for us, because something as simple as water can break down these reagents and they're no longer organometallics anymore. So one of the key things that I always tell people is that when you work with organometallics in the world of lithium or in the world of magnesium, especially magnesium, is that water cannot be allowed and everything has to be super dry, which means that maybe even water or moisture from the air in the room can start making these reagents decompose on themselves. So very often we have to make these fresh. But they're not very difficult to do. Honestly, it's not very difficult to do. So let's take a look at lithium. If we have to make a lithium organometallic, because we have to make one in order to react with one, get it? How would we do that? Well, number one, of course, you need some type of lithium source. You need lithium. Number two, you typically are going to bring in some type of alkyl halide. So RX, X, fluorine, chlorine, bromine, iodine. So we've talked about alkyl halides for quite some time. That's what we focused our substitutions on. It's what we focused our eliminations on. It seems like everything that we do has an alkyl halide in it. And then three, we need some type of solvent, right, to get these two things to mix together. We need a jacuzzi tub so that lithium and this alkyl halide can fall madly in love. So the jacuzzi tub that we're going to be using is a solvent, and this solvent will typically need to be nonpolar. Polarity is the problem here. That's why water's not going to work. So if we can find something that's nonpolar, it's got to be nonpolar because that's an organic. But we also want to make sure that it's not acidic. And that's the problem with water. It can donate a proton. Well, the best conditions for the lithium reaction is a solvent that's hexane. Okay, and you know how to draw the structure of hexane. Hexane means 6. So 6 carbons in a row. 1, 2, 3, 4, 5, and 6. So hexane is an organic. It is all carbon. It's all hydrogen. There's no polar groups on the thing. There's no reactions that we can do with it very well because there's no double bonds or triple bonds or OH groups or halogens on it. It is just an organic that is a soup, a liquid, a jacuzzi tub that allows the alkyl halide, which is reactive, and the lithium, which is also reactive, to come in together. And this is the proper setup for our lithium-based molecules. Once again, I need to make the metallic before I use the metallic almost every single time. All right, so there's our lithium. Well, magnesium follows the same suit. No water, nothing acidic. We need a good solvent. We need to make sure it stays completely dry. All of those still stay true with magnesium. That's why we lump these together. So for these, as you can imagine, we need to use magnesium. And magnesium will typically come in the form of magnesium turnings. And turnings are little strips of magnesium that are cut really, really tiny, maybe crumpled up like an accordion. Kind of cute. shiny, really thin. Once I get my magnesium, well, guess what? I need an alkyl halide. And that alkyl halide and that magnesium, they need to react together, but I need a jacuzzi tub so they can get to know each other, and that jacuzzi tub is going to have to be filled with a solvent, and that solvent is not going to be hexanes here. I need the same concept. I need a solvent. I need something that is not going to carry any kind of proton. But with magnesium, it's different than lithium. And the reason is because magnesium needs to be stabilized a little bit more. And what will bring stabilization to this is a little bit of electron pairs. So hexanes is not really a good choice for me. There's no electron pairs there. What is a good choice is something like ether, some type of ether. And ether is also known as diethyl ether. Diethyl ether is 2 carbons. There's the ethyl, and di means 2 of those. So here is, it looks like a crow to me, or some type of seagull, right? So there's the diethyl ether group. And if you don't want to use ether, THF is also another solvent that's commonly used with our magnesium form. And THF, if you've had me for Organic 1, I called the cupcake molecule. And here's the cupcake molecule. And this thing has on some electron pairs, just like ether does. So very similar to why we use them. Oxygen, electron pairs, it stabilizes the magnesium. That magnesium needs it because of the way that it forms. Lithium does not, though. We'll see that. We'll see the difference. But here are the 2 structures for the 2 solvents that are typically used in an organomagnesium compound. Magnesium is used very often. It's probably one of the most common metals that we use in a laboratory. And for that reason, we have a special name that's given to these. And these are called Grignards. These are Grignard reactions. So if you hear someone to say, I need the Grignard, okay, well, that basically means they're working with magnesium compounds. If someone asks you, this reaction needs to undergo a Grignard reaction in order to form this product, they're talking about a magnesium-based organometallic reaction. It's just a name that organomagnesium goes by. I don't know about you, but Grignard is much easier to say than organomagnesium compound. And because they're so common, and because we use them very often, well, if we have to say organomagnesium compound all the time, my mouth is going to get tired. I'm not going to want to say it. So Grignard is a much simpler way to discuss the same types of things that magnesium brings to the table. It's just a different name. That's all that it is. So again, the preparation of the Grignard, or the preparation of the lithium-based compound, is really up front and center. All right, so what we see here is basically this idea of making the organometallic. So in the top one, here is my alkyl halide. It's 1-bromobutane. Bromo, there's my bromine, and butane. 1, 2, 3, 4. 4 carbons. So 1-bromobutane. And I'm going to react that with lithium with some hexanes. And we said hexane was a solvent. That's the only purpose of it. So this lithium, I've got to bring 2 in. And the reason is because one of the lithiums will go onto the organic and stay. And when this lithium comes on, this bromine's going to be, pop, off it goes. Well, this bromine's negative. It's not going to just want to stay around. We need something to kind of distract it a little bit. I mean, the bromine's single. We don't want it to be single forever. It's floating around in solution. It can cause us problems. So that's the purpose of the other lithium. The other lithium will come in and say, hubba, hubba, and then off it goes and makes a product. So that way that bromine is not going to cause us a problem from this point on. And here we have our butyl lithium reagent, and this is our organometallic that we can then use for other purposes. So I'm going to make this in a lab, and I'm going to make it as I need it, and then I will use that fresh butyl lithium in order to react with something else and do something else with it. So that's the process that normally happens here. Down below, you're seeing the same thing, except instead of a straight chain, they're putting it on a benzene ring. And they're letting you know that these things on benzene rings are okay. It's an aryl halide. And for the most part, all of the above, as far as carbocations and types of halogens go, will work with these things. Secondaries and primaries, and even the more weird ones like the aryls that we've talked about, or the Venlics that we've talked about before in Organic 1. So really, there's nothing that we have to watch out for. For the most part, these are going to do what we want them to do, which makes them kind of nice. So here we have chlorobenzene. Chloro is directly attached to a benzene ring. And once again, we bring in double the amount of lithium. And the reason we bring in double the amount of lithium is because one of those lithiums will go on to where the carbon was. And whee, off it goes. They make a new relationship. And then that other lithium is going to be freed up in solution. So when this chlorine gets spit off, that lithium and that chlorine, hubba hubba, and then we go and make another product with that. And we kind of distract chlorine for a little bit. So that way chlorine doesn't do anything crazy and tries to come back and react with that compound again. So this is the whole mentality of making the lithium-based organic that we will then use for other purposes. These are not going to stay around very long, folks. Okay, that's the thing that you got to keep in mind. They're not going to stay around forever. And that's why we make them fresh, and it's nice because they're very easy to be made fresh. So we do them as we need them. Okay, well, that's the lithium side. We have also talked about the magnesium side. So how does the magnesium side change a little bit? Well, not by much. Notice we don't have a 2 here. There's a 1, and this is the reason why. Lithium carries with it a +1 charge. Magnesium carries with it a +2 charge. Okay, so this is what happens. Cyclohexyl bromide, which is our alkyl halide, we said anything's pretty much fair game, will react with magnesium. Okay, so what happens is that this carbon says, magnesium, come on, I'm going to take advantage of you because you're easy to take advantage of. And I'm tired of this bromine keeps sucking my electrons away. So it's my turn now to flip the script. So bromine, boom, off it goes. And magnesium comes in and takes that spot. But magnesium carries with it a +2 charge, not a +1 like lithium did. So when that magnesium, and here I'm going to draw the ring, when this magnesium goes on, that magnesium's not quite happy. And the reason that it's not quite happy is because there's still a charge there. And that magnesium says, hey, bromine, before you go, why don't you come back for a minute? Because I like to see you too. And we get this magnesium bromide compound that forms because of that. 1 bond to the carbon, 1 bond to the bromine. And this is how the magnesium is different than the lithium. And this is what we call our Grignard reagent. That magnesium-based molecule is our Grignard. Well, the same thing happens down here with our vinyl. Remember, sometimes vinyl didn't work. And here it does. We don't have to question it. So just like before, bromine, pew, off it goes. Magnesium comes in and carbon says, I'm going to take advantage of you. And that magnesium goes in and we form a bond. But as that bromine's leaving, magnesium is going to whisper in bromine's ear, psst, hey, stay around a little bit because I like you too. And we have kind of like a little three-way going on here. Magnesium is in love with the carbon and the bromine at the same time, and it sees each other both. So we form these magnesium bromide compounds, which are called our Grignard reactions, here and here. All right. These solvents are a little bit different, and here's why. The solvents in this case, notice diethyl ether. So we said here was diethyl ether and THF, my cupcake molecule, because there's my little cupcake with a cherry on top. All right, so there's my THF and my diethyl ether. These two reagents, or solvents really, these solvents carry with it these electron pairs. And those are needed. And the reason is because magnesium is still greedy. All right, this magnesium has a bond here and a bond there. And this is slightly unstable the way that it is. So what happens is that the oxygens from the diethyl ether will come in and just say, hey, you want to hang out for a little bit? And this stabilizes the magnesium. So that way it stays on to this organic, which is where it's connected to right now. Otherwise, this magnesium could possibly go out and look for other things in order to get somewhat like that octet charge that all of these smaller atoms want to have. The same thing happens with THF. So this THF is bringing that oxygen to the party, and that oxygen's coming in, and that oxygen is just hanging out with that magnesium for a little bit. It's just stabilizing it. That's all that it's doing. It's not reacting. It's not forming a full-blown bond or a full-blown product. It is just there to help stabilize everything that goes forward. So this is the production of our first two organometallic compounds. Now, we have not done any reactions yet. You need to understand that, okay? No reactions have been discussed with these metallics at this point. What? But I'm seeing arrows and reagents and product. I know, but that is the production of the metallic that we will then need to use for another purpose. That's the only thing that we've done so far. So in the upcoming videos, what you're going to see is that this product that we have generated here, or this product that we've generated here, that is going to be used in a reaction, and that will be a reagent with something else, and that will form a product. But a lot of people question, where do those things come from? Where does that magnesium compound come from? Where does the lithium compound come from? And this is how they're made. So very often we have to do this step in a lab. If I'm following a Grignard lab experiment, it will tell me to make the Grignard first. And I will go through and take the magnesium turnings, and I will use the proper solvents, and I'll allow this thing to form. And then I'll use that in addition to something else that I want to react with to get the product that I'm actually after. And that's why we discuss the generation of these organolithium or organomagnesium compounds. Because a lot of times you got to do them. So why not talk about them? Why not talk about how they form and the purpose of the solvents and stuff? Because if you're going to do these in the lab, and you will have a lab experiment that will make you do one of these, then we need to kind of at least know some background with them. And here's your background. All right, so that's where this video is going to stop. Again, we're trucking on a little bit. We're getting a little used to the waters here. We're taking our time. We're taking baby steps. And then eventually we'll put these guys to work. We'll put these metals to make a job, to do a job that they were meant to do. So they're not just going to stay around on the couch and watch TV and eat potato chips all day. And we're getting ready to kick them out and do something for us. So next video, we'll figure out what that's going to be.